Imagine you're reopening a project that you worked on a few months ago. Let's say you're a psychologist and you've been studying the impact of remote work on employee mental health. You collected survey responses, conducted interviews, and started analyzing the data. Now you're going back to pick up where you left off, but as you open the files, you quickly realize that things aren't as clear as you remembered. You open the project folder and it's a mess. There are files named Survey Analysis version 1, Survey Analysis version 2, interviews.csv, and tempcleaning.py, but they're not organized in any meaningful way. It's hard to tell which files are raw data, which are analysis, and which are just duplicate versions of the same thing. You can't remember why certain files exist or what changes were made between them. Then you open one of the Python files, thinking that that's where you did the analysis, and you quickly realize it's a mess. The code is doing something, but it's unclear what and why you chose certain statistical transformations. There's no documentation or comments explaining what's going on, and you're left trying to reverse engineer everything just to understand your own thought process from a few months ago. Now, imagine you had organized this project more clearly from the start. Let's think about how you could have set it up so that you don't run into these issues next time. First, everything could be organized into clear folders. The data folder could be split into raw data and process data. The notebooks folder could hold each stage of your analysis, like cleaning, analysis, and visualization. And the source directory could contain the scripts that handle data manipulation and modeling. This structure makes it easy to find exactly what you're looking for when you revisit the project. Now, what about the code itself? How could that be more organized? Well, the code could be cleaned by breaking the code into functions with very clear names. The functions could be small and modular, and the logic should be easy to follow. You would add documentation to explain exactly what each function and file does, so that when you come back to it, you're able to quickly understand your own code. So what's the big takeaway here? Clean code and proper file structure research much easier. When your code is organized and your files are well structured, it's easy to track your progress, collaborate with others, and pick up right where you left off, even months later. You save time, reduce errors, and focus on your insight and analysis rather than spending time figuring out how everything works. And if someone else wants to work on your code, they'll have a much easier time understanding and modifying it. Think of it as a form of self-care. Do it for future you. Messy code can lead to technical debt where fixing something takes way longer than just rewriting it from first principles. Trust me, your future self will thank you. First of all, what even is clean code? I'm going to quote the classic book Clean Code by Robert Martin, who's also famously known in the computer science world as Uncle Bob. Uncle Bob writes, "Code is clean if it can be understood easily by everyone on the team. Clean code can be read and enhanced by a developer other than its original author. With understandability comes readability, changeability, extensibility, and maintainability. Clean code is simple and direct. Clean code reads like well-written prose. Clean code never obscures the designer's intent, but is rather full of crisp abstractions and straightforward lines of control." So that said, let's talk about easy tips that can make your code much cleaner. Principle number one is to use meaningful variable names. The names of your variables should clearly convey the purpose or role of the variable, which makes the code much easier to read and understand for anyone who comes across it. For example, instead of using generic names like temp or data, try to be specific. And consistency is also key. Use a consistent naming convention, such as camel case or snake case, to maintain uniformity throughout your code. For example, let's say we have a variable that's a list. First, we can call it data. But what does data represent? We don't know. Let's make it much more specific. Student scores. That makes it much easier to follow. Or, for example, let's say we define x equals true, but that doesn't give any clarity, and someone trying to follow code later could get very confused. What does x represent? Is it a flag or a status? It's not clear. A better approach would be to use a more descriptive name like is outlier equals true. Now it's very clear what it does. Principle number two is to break code into functions that do one thing only. For example, if a function's job is to read data, don't make it handle processing too. For example, let's look at the code file on the left. That's pretty hard to understand, right? But when we look on the right, we see that it's neatly broken into functions that are easy to follow in the main function. It's like reading a story and very easy to follow. Principle number three is that assertions are a great way to preemptively catch errors. Assertions make sure that what you expect to happen actually happens, and they're a great tool for debugging and ensuring that your code is correct. In Python, we use the assert syntax. So for example, the function below calculates the mean of a list of numbers. But first, it uses an assertion to check that the provided data list is not empty, and if it does, it will quit with the message data should not be empty. Then it uses an assertion to check that every element of the list is actually a number. And if there is an element that is not a number, it quits with the message all elements must be numbers. This way, we prevent errors or incorrect calculations due to invalid input. In R, we can do the same thing using the stop if not function. Principle 4 is to use type hints. Type hints are a way of making your intentions clear to anyone reading your code, including your future self. They tell exactly what kind of data you should expect to go in and out of your functions. For example, in the function below, it's not clear what type data and threshold should be or what the behavior of the function is when remove above is set to false. But if we add some type hints, it becomes much clearer. First, we see that the first argument, data, is a list of floating point numbers. And then we see that the threshold is also a floating point value. And then we see that the default value of remove above is set to true, and it's a Boolean, so it can either be set to true or false. Lastly, we can see the return type, which is that the function will return a list of floating point numbers. This helps us understand what to expect when we use this function, instead of having to read the function every time to understand what it's looking for. Principle number 5 is to use consistent formatting. Whether you use tabs or spaces, stick with one and don't mix them. Choose a line length limit and make sure your functions and variables follow the same naming conventions throughout your codebase. Tools like Black or AutoPep8 in Python can help auto-format your code so you don't have to think about it. Also, most IDEs can do this automatically, and many people have format on save enabled in their IDE. On the left, we can see some very hard to understand code in Python that's hard to understand simply because it's not consistently formatted. On the right, we see how much easier it is to follow. Principle number 6 is to avoid magic numbers and to use constants instead of numbers in code. Magic numbers are hard-coded values in your code that don't explain their purpose. For example, if we're randomly multiplying by 42 in your code, it's hard to understand why it's doing that. Instead of using the number 42, instead we could use a constant with a meaningful name to make the code more readable. For example, if we define discount percentage equals 0.1, then when we calculate the discount, we see that it's easy to understand what it's doing. It also makes it much easier to change the discount percentage everywhere in that one line rather than change the 0.1 everywhere where it appears. Now, principle number 7 is DRY, which stands for don't repeat yourself. This principle is about eliminating duplicate code. If you find yourself writing the same thing more than once, it's probably time to create a function or reusable piece of code to make your life easier. So for example, if you're reading CSVs repeatedly, instead of using the same complex code every time to do it, you can just make one function called, let's say, read and process data, and then use that every time. While these are great principles, every programming language really has its own coding style and best practices, so what's considered clean in Python may not necessarily be clean in R or JavaScript. For example, in Python, snake case is typically used for variable names, whereas in Java, you'll see much more of camel case. These language-specific conventions make code more consistent and easier to read for developers familiar with that language. But how do you know what the right style is for the language you're working in? Well, each language has its own official style guide that lays out the do's and don'ts. For example, in Python, the official guide is called PEP8. It's a set of recommendations about everything from indentation to line length to naming conventions. R actually does not have its own guide, but there are some external ones like Google's R guide, and there's also a tidyverse style recommendation for writing readable and consistent R code. Now that we've talked about writing clean code, let's talk about files and file structure. First, let's talk about README files. It is essential to include a README file in every project. README files not only provide essential information about your project, but it helps people understand how to set it up and use it and contribute to it. Whether you're working alone or with a team, the README is often the first thing people see, so make sure it's clear and informative. A good README serves several important purposes. First, it's a project overview. It gives a summary of the project and its goals. If someone is looking at your project for the first time, the README helps them quickly understand what it does. Second, it provides instructions on how to set up the project, install dependencies, and run it. If you're working with others or if someone wants to contribute, the README makes it clear how they can get involved. Third, it's a form of documentation. It often serves as the central place for key information like how to use the project, code structure, and how to report bugs. Now, file structure refers to the organization of files and directories in a project. It's like how you organize your room. When everything's in the right place, it's easy to find what you need. But when things are just thrown around, good luck finding anything when you need it. The same principle applies in code. Good file structure keeps everything neat and easily accessible. A well-organized file structure makes your project easier to navigate, scalable, and collaborative. So for example, instead of having a giant mix of files without any rhyme or reason, we could create a very neat file structure. Let's say a code directory for core scripts, functions, and models, a data directory for raw, processed, and results data, a notebooks directory for Jupyter notebooks or similar files, and maybe a test directory for unit tests. Now that wraps up our intro to clean code. But clean code isn't complete without making sure it actually works, and that's where testing comes in. Stay tuned for our next video where we'll dive in to how to properly test your code, make sure that it's working as expected, and catch bugs before they hit production.